Hello, I'm Patrick Balducci, Chief Economist at Pacific Northwest National Laboratory. Today I'll be covering energy storage applications in the United States with a focus on how the use of analytics can improve the value proposition for energy storage in the U.S. I'm also the head of the Energy Storage Analytics team at Pacific Northwest National Laboratory, and I lead a terrific group of researchers that includes other economists, engineers, and physicists. You know, when I began exploring this topic, I evaluated the sort of landscape of literature, reports, and simulations and models that were performing research into the value of energy storage. And it seemed to me that I was sort of stuck at the beginning of that process because every path I went down led me to a place that I didn't want to be. And it occurred to me, or it seemed to me, that what we need to do is think about these values more fundamentally. And so with this in mind, we've been evaluating energy storage projects across the United States and gaining valuable lessons as we do so. And today I'm going to share some of those lessons with you. I think historically, many of the benefits have been poorly understood and overstated. So in one way, historic assessments of energy storage systems have missed several of the benefit streams that actually accrued to energy storage systems, but at the same time, those that were evaluated tended to result in benefits estimates that were overstated. So energy storage really is critical for a flexible future grid. The grid is becoming more green as renewable portfolio standards expand across the United States, and particularly in the western United States. And also, the grid is becoming more distributed in nature as new renewables are deployed down in the distribution system and smart grid applications and technologies take effect. Effectively, where we could once rely on predictions of generation and it was more challenging to evaluate load, now it can be challenging both on the generation and load side, which creates uncertainty in the grid. So for the planning of the future grid and the operation in real time, energy storage becomes an enormous asset, either through supplementing hydro, doing low water reserves, or providing backup power for critical infrastructure or remote communities, or balancing load and generation as you begin integrating renewables. Energy storage, while expensive, provides enormous value to the grid, and so it's really been our focus on assigning value to each of these services. So there are many unique attributes associated with energy storage. It can be deployed anywhere in the grid. It's modular, it can be scaled up, it provides bidirectional flows of energy. It can serve as generation and load effectively. And so any simulation has to account for all these unique attributes. Before we really get into the topic in more detail, I want to give you an overview of a few just basic concepts that will help guide us through this conversation. First of all, energy storage systems provide services or values. So a use case is an application specific to an installation that provides a defined value to the grid and community. So buying low and selling high in the energy storage, or in the energy market, is a value stream. Or providing backup power to a critical facility, or in a microgrid setting, is a value stream. Energy assets, of course, come in many forms, and the technologies must be carefully characterized. So information you may hear from a manufacturer or a vendor may not actually add up when engaged in economic operation and the energy asset is deployed out in the field. And so we spend a lot of time trying to improve the characterization of the performance of particularly energy storage systems and then weaving those lessons back into our economic optimization. Value comes in many forms, and we've developed a taxonomy, and there's 5 categories of benefits. Bulk energy, which includes buying low and selling high in the energy markets, and capacity, that's providing resource adequacy or that capacity for that peak increment of load. And then there's a variety of ancillary services that are often traded in markets, but even outside of markets, resulting costs to vertically integrated investor-owned utilities and other utilities that have to provide these services. So things like frequency regulation, which is making sure that load and generation are balanced in real time, and several others also are falling under this category. transmission level benefits, transmission congestion relief and asset deferral, distribution deferral, voltage support, conservation, voltage reduction, and outage mitigation or resilience benefits accrue at the distribution level. And then behind the meter for customers, you can manage your bill, reducing demand charges, improving reliability. And all of these values are complex and differ from one region to the next. And when simulating them, have different needs that must be modeled accurately. Effectively, the energy storage system cannot provide all services simultaneously, and so sophisticated modeling is necessary to make sure that you can actually stack these benefit streams reliably. And then finally, it's important to establish an accounting basis, because if you're improving resilience from the perspective of the customer, the benefits accrue to them. And if you're improving it from the perspective of the utility, that's a different stream of benefits. And so whenever we perform these analyses, we make sure that we're accounting for the benefits appropriately. Either the costs are accruing to the customer and the benefits to the customer, or more broadly to the utility and customer, or we're focused on the utility. Sometimes we can evaluate it from a societal perspective as well and include things like emissions benefits, so reducing carbon, for example. Today we have a very broad program at Pacific Northwest National Laboratory. We're evaluating 16 energy storage systems across the United States. It includes many different forms of energy storage. We're evaluating everything from lithium-ion battery systems to redox flow battery systems, small and large-scale pump storage hydro systems. We're evaluating power-to-gas systems, so hydrogen, and also fuel cell technologies as well. So anything that can effectively store power and then provide it back to the grid, from our perspective, is something worth studying, and important studying, and a potential important asset in the future grid. We're evaluating 16 sites, 1.6 gigawatts, 18.2 gigawatt hours of storage. So when I say gigawatts and gigawatt hours, what I'm saying is that at any given point in time, these energy storage systems could collectively provide 1.6 gigawatts of power to the grid. When I tell you that it's 18.2 gigawatt hours, that means that's how much stored energy there is. So if I'm evaluating a 1 megawatt, 4 megawatt hour energy storage system, that means if it functions properly, that storage system could provide 1 megawatt of power for 4 hours before being depleted. So here are a taxonomy of energy storage services. I've mentioned these already: bulk energy services, ancillary services, transmission, distribution, and customer energy management services. And for each of these value streams, we've defined methods and developed models and tools for evaluating those benefits in isolation and then co-optimizing between them. And I'll get into that more in just a few minutes. One of the things we did first was we completed an expansive literature review and conducted a meta-analysis. So you can see the y-axis being service value in terms of dollars per kilowatt per year. So for example, at one location, if we had a 1 megawatt battery system and it could generate $100,000 in annual value associated with capacity benefits, then the metric here is dollars per kilowatt per year, which would measure at $100 because there's 1,000 kilowatts in 1 megawatt of energy storage capacity. And you know, arbitrage was historically thought of as the principal value for energy storage, right? It makes sense that with an energy storage asset that effectively you store energy and then you release it later. So of course, you're going to generate an enormous amount of value through arbitrage. But in fact, what we found is that that's one of the lowest value streams. And that's because energy storage systems incur losses. So round-trip efficiency means that whatever comes from the grid into the energy storage system and then cycled back to the grid, that you're going to lose some of that. So when you say 90% round-trip efficiency, then in the round trip going to the grid, to the energy storage system device, and then back to the grid, you're losing 10% of that energy. It's lost in the transfer. And what we find is that while you may hear from vendors that you can get 90 to 92% round-trip efficiency, when engaged in economic operation and including all power conversion systems and including standby losses, auxiliary loads, that number begins to dive and can get into the low 80s and even into the high 70s, and that it differs from one application to the next. And so it's important to understand how these different characteristics apply to different services or value. Frequency regulation, you can see there's a great degree of variability from one region to the next, and what you're seeing there with those box and whisker plots is with the box, 25th to the 75th percentile, and then the min and the max in the whiskers. And this is based on between, typically 30 to 50 studies that were conducted of energy storage systems for many of these values. Some of the values, much less so. But energy storage systems are extraordinarily efficient at providing frequency regulation. That's where the load and generation is brought into balance. Energy storage systems are exceptional at following fast fluctuating signals that are shared with markets or regional operators. And also resource adequacy or capacity. This is based on the cost of a new entrant, the next best alternative of providing this service. They tend to aggregate around the $80 to $120 per kilowatt per year value. And so for each of these values, you can see a great degree of variability and some much more higher than others. And the last I want to touch on is transmission and distribution deferral benefits. In most cases, when we examine energy storage systems, there are no transmission and distribution deferral benefits. We go through a screening process, so it's highly variable. But for some specific applications, like on Nantucket Island, that I'll mention in a few minutes, the value is enormous. Deferring an investment in a $150 to $200 million submarine transmission cable for up to 13 years generates tens of millions, over $100 million in present value benefits from the utility perspective. Okay, let's just run through a few of these example use cases. Energy arbitrage, which I've already mentioned. Within markets, you can download historic locational marginal price data, like in California for California ISO LMPs. In the Pacific Northwest, we rely on the Mid-Columbia energy market. The value obtained is by purchasing the energy during off hours, during low load hours, off-peak hours, and then providing it during peak where prices are much higher. Once again, you have to account for the efficiency. And to the extent that you're overestimating your round-trip efficiency, you could be bidding into a market thinking you're getting 90% round-trip efficiency when in fact you're only obtaining 75% and you're losing money. And so capturing that value in real time is actually quite challenging because you have to accurately predict those LMP changes and then accurately characterize the performance of your battery system when you engage in economic operation. Particularly in real-time markets, that can be quite challenging. Capacity or resource adequacy is another important benefit from the perspective of energy storage, particularly if there's needle peaks. So the way the grid is organized is that just like a transportation network, for the vast majority of hours, you have plenty of capacity to meet all the needs of the consumers. But during a small number of hours, when the load surges or when traffic surges, you have inadequate capacity to service those very scant number of hours. In the energy sector, you still have enough capacity because you have actually reserves and a buffer there. But still, you have to build the grid in a much more robust manner with much more generation capacity to serve a small number of hours. So energy storage systems can actually just store the energy and then provide it when you need it most, fairly effectively. And some capacity markets trade this value here in California, for example, or in ISO New England market. There's a forward capacity market. For regulated utilities, once again, it's based on the next best alternative, which tends to be a peaking combustion turbine. And while those may cost $150 to $200 per kilowatt per year, once you build out the flexibility benefits associated with those and you account for the incremental capacity equivalent of energy storage, that number is reduced typically to around half of that value. And that's because if you have a 2-hour energy storage system, meaning say 1 megawatt, 2 megawatt hour energy storage system, it's just not as robust and won't cover as much of the peak when you need it as would a more traditional combustion turbine. All right, frequency regulation. I've already mentioned this very important value stream for energy storage. So energy storage systems are exceptionally effective and efficient at providing this service. It tracks a second-by-second adjustment in output power to maintain grid frequency. So you're following what's called an automatic generation control, or AGC, signal. And there are effectively 3 components to this value stream: capacity. So how much capacity for the energy storage system are you bidding in on an hourly basis? So if you're bidding in 10 megawatts, you get credit for all 10 megawatts. And unlike a traditional generator that effectively has to operate in the middle of its operating capacity, an energy storage system can go a full 10 megawatts up and 10 megawatts down when it either charges or discharges. And then as energy flows through the battery system, as you can see on this chart, you can see the green bars, when energy goes into it and then out of it, effectively it's like a string, that once you pull it taut, that's what's called a mileage component, mileage or service fee, and you're paid for that as well. And then finally, the performance benefit. So if you have a 95% performance rating, whatever value that accrues to the grid and you collect in the market, the value would then be derated by 5% because you didn't fully track that signal with 100% accuracy. Energy storage systems do that quite effectively, and so they do tend to reach into the 90s and in some cases into the very high 90s, and so they have very little duration as compared to traditional generation assets. Another benefit stream is outage mitigation. The way we evaluate this, well, we can evaluate it from the perspective of the utility in terms of reduced penalties and fines associated with poor performance or through lost energy sales, but mostly we evaluate it from the perspective of the consumer. So what we can do is either using distribution systems like GridLab-D or OpenDSS, we can model the distribution system or we can make assumptions about that distribution network. And then what we do is we simulate the operation of the battery for a 1-year period. We layer in this benefit stream by performing a statistical analysis of historic outages on that feeder or feeders, wherever the energy storage system is located. And then we create a statistically average outage year, and we layer in economic information. So the cost of outages, which we obtained from Lawrence Berkeley National Laboratory and through their interruption cost studies. And what that establishes is a value of loss of load for 3 customer types: residential, small commercial industrial, and large commercial and industrial. And we simulate those outages, either with perfect foreknowledge, because we assume that with inclement weather on the horizon, you can charge up to 100% state of charge and keep it there through the event, or with no foreknowledge, in which case, whatever energy happens to be available in the energy storage system, that's what we bring to bear on the need. And when we simulate it, we then show the cost of the outage accruing to the customers with and without the energy storage system. So if you take it from a 2-hour outage down to a half-hour outage, we can calculate the economic benefit to customers in that area. Another one is transmission and distribution deferral. In utility accounting, we think about a value in terms of present value. So for all of you who have taken an Economics 101 course, you can see the very well-known present value equation here, future value divided 1 plus the interest rate raised to the n number of years into the future. And so in the denominator, the interest rate in this case is going to be the weighted cost of capital for the utility when we're evaluating the benefits from a utility perspective. So that could be 6 to 7% that you're actually reducing the present value economic costs each year. And of course, as that grows over time through compounding, that number can be quite large. And on the numerator, you see the future value is only growing at inflation. So that may only be 2 to 3%. And so you've got a number growing in the denominator much quicker than the number in the numerator. And as a result, if you have a deferral of, say, 5 to 10 years, the benefits can be quite enormous. I've got an example here, a $10 million substation that we were allowed to defer for 6 years. It brings the cost and present value terms from $10 million down to $7.5 million. So that's a 25% reduction in costs from a utility accounting perspective. Bundling services, how to do it optimally. If we just evaluated each of the services individually and then summed them together, we would vastly overstate the benefits associated with energy storage. You cannot provide all services simultaneously. Effectively, there's interdimensional competition for the energy in the energy storage system. If you provide some energy in this hour, there's less of it available in the next. And then also you can't meet the needs of all services simultaneously. And so with our simulations, a decision has to be made. And so you can see in the chart to your left an energy price. If you're only providing arbitrage, you would buy in the early morning hours and then discharge at the lunch hour and then in the evening hours to take advantage of relatively higher prices. As you layer in one benefit stream after the other, so balancing or frequency regulation, T&D deferral, and then finally volt-VAR control, effectively you see this deviation from that initial charging and discharging schedule in the second panel to one that's much more complex in the fifth panel. So accounting for that is quite complicated and requires sophisticated modeling capabilities. And so you can see to your right there, how as we toggle throughout the day, effectively there's this constant tabulation happening where arbitrage is being either credited in the form of energy payments or debited in the form of energy costs, and then balancing is overlaid from there. And then in this example, there's an outage that results from a disruption in the afternoon. And you can see the value there is in thousands. So for a small number of benefit streams like capacity or transmission and distribution deferral or outage mitigation, those values for a discrete event can be quite enormous. So let me run you through a few case studies and how the use of analytics could have improved their value proposition quite significantly. So the Portland General Electric developed the Salem Smart Power Center using ARA money, so stimulus money from the federal government. You know, lithium-ion technology was more of a nascent stage of deployment at that period. This was about 10 years ago, I think, when this project was initiated. And the cost when it was ultimately deployed was about $20 million, which is quite a lot for a 5 megawatt, 1.25 megawatt hour lithium-ion battery system. In those days, of course, it was an appropriate cost. Today, the cost would be probably less than a third of that amount. And you'll also note that at 5 megawatts, 1.25 megawatt hour, it's quite a shallow energy storage system from an energy to power ratio perspective, meaning that if you provided 5 megawatts continuously, you would fully deplete the battery's energy capacity within 15 minutes. And that has significant implications for the economics of the system. So when we were hired to help PG understand how to best use the Salem Smart Power Center, at the time, the system was only being used for what's called primary frequency response. So it sits there idle on the ready when there's a significant voltage sag in the western grid. And then it responds. And there was enormous value from that perspective. And it really is the number one value stream for this energy storage system. So Portland General Electric was using it wisely in that regard. But it was not being used for anything else. And so we were evaluating other potential applications associated with this asset. So something we learned in the process is that, as you can imagine, an energy to power ratio of 0.25 doesn't give you much to work with. And so if you're talking about energy arbitrage, once again, you can only, effectively use a fourth of the power capacity of the energy storage system in any given hour because you only have 1.25 megawatt hours of energy to play with. Same thing with frequency regulation and many of the other benefit streams. And when you look at that bar chart to the left there, you'll see that first we evaluated each of the value streams individually. And we get roughly $7.5 million. But then when we co-optimize between each of those services, that is to say we simulate operation of this system in the grid, and we only provide what is technically achievable to provide, you can see the benefits fall to about 5.8 million. So you reduce 25 to 30% of the benefits by doing a proper co-optimization process. And then you can also see that at current prices, with the ROI, you're still underwater effectively. You're well below 1.0 at a return on investment ratio of about 0.78, I believe. But if you sized it correctly, with an energy to power ratio of 2, you could generate a return on investment of 1.24. So doing a economic assessment before you actually deploy the energy storage system is incredibly important. Here's another recent project that we completed. Shell Energy North America hydro battery system. This is not a battery. It's a small-scale modular pump storage hydro unit. So in the U.S., pump storage hydro effectively has reservoirs on top of a hill and reservoirs or a lake or river on the bottom of a hill, and the water is pumped up the hill or through the hill effectively when during off-peak hours when you can engage the pumps and get the water back up the hill at low cost. And then the water is allowed to flow down and through the turbines and back out during peak periods to generate electricity. The problem with these systems is that although they're very efficient and they have enormous benefits in terms of huge capacity, often in the hundreds of megawatts and even more, gigawatt of power or more, and gigawatt hours of energy storage capacity, they're exceptionally expensive, often exceeding $1 billion in cost. And also the environmental restrictions are quite challenging to overcome. And so none of these large-scale pump storage hydro systems no new large-scale pump storage hydro systems have been deployed in the U.S. in the last 20 years. So to get over these challenges, Shell Energy North America has developed a small 5 megawatt, 30 megawatt hour modular pumped hydro system, which they call the North America Hydro Battery System. And we evaluated this system in 4 locations across the United States: in Washington State, in Hawaii on Oahu, in California ISO market territory, and several different locations in the New York ISO territory. And the red diamonds show the costs of the system today. Future costs will be driven downward based on estimates from Shell Energy North America. And then you can see the bar charts for each of these various locations. And while for most of the locations, the return on investment ratio is under 1, it's important to demonstrate how the value changes from one location to the next. And so in California, the benefits are largely tied to frequency regulation and arbitrage, so energy and balancing. And you can add in an additional benefit called flexible ramping, so responding to afternoon sags in generation capacity of the PV or photovoltaics and solar at a time when loads are coming back online as people come home. And so those are the important benefit streams there. In the Northeast, it was driven predominantly by capacity need. And so from one location to the next, the benefits differ quite significantly, and you need tools that can adequately capture each of these benefit streams. So the last project that I'll mention is the Nantucket Island Energy Storage System. So on Nantucket Island, there's a small resident population of about 11,000 people, and during the summer months, the population can swell to over 50,000 people. Effectively, it becomes a very hot tourist destination during a small number, really 2 months during the summer. And as a result, load surges during those months. And right now, if National Grid, the provider that serves the island, does nothing, there'd be a number of hours where load would enter what's called an N-1 contingency window. So that is to say that if load surges beyond a certain point and one of those submarine transmission cables go down, there would be insufficient capacity to serve that load and the system could crash. And so National Grid explored 2 options. One was a third submarine transmission cable at a cost of $150 to $200 million. And then the second alternative was a 16 megawatt, maximum 16 megawatt, it's temperature dependent, and combustible turbine generator, and a 6 megawatt, 48 megawatt hour, what was ultimately a Tesla lithium-ion battery energy storage system to provide that peak service during those 2 months. And so they understood that that was the primary benefit stream, but they wanted to know what else they could do with this battery energy storage system. And also, could they bid it into regional energy markets, and what would the value of that be? Now, historically, a system that's rate-based, so built into the rate structure, cannot also be bid into markets. FERC has demonstrated a willingness to consider an option of taking a rate-based asset and bidding it into energy markets, provided the benefits of the energy services it provides flow back to the customers while still maintaining the primary use of that system. And so that's what we evaluated from the local customer's perspective for National Grid. So benefits of local operations. Well, we performed an extensive load analysis so that we could effectively simulate when the grid would enter that N-1 contingency window over the economic life of the battery system, which is 20 years. And we also modeled the entire National Grid distribution system on Nantucket Island. We evaluated historic outages. There were over 700 outages over 12 years, which is a quite large amount. And then we were able to break it down to the number of outages that could actually be addressed through the combustion turbine generator and the energy storage system working together. And we could make suggestions, recommendations with respect to improvements in their local grid to ensure a full export of energy through reconductoring of some of the lines, and also for a faster response in the event of an outage. So automated line switching, for example, rather than what they have today, which is manual line switching. And so we simulated all these outages and found that local operations generated enormous value, most of which was tied to transmission deferral, almost $110 million, where this was 13 years of benefits, 2% in terms of the growth in the costs over those 13 years, and it's compounded, so 1.02 raised to the 13th power. And then the denominator, the weighted cost of capital for National Grid, which I think was about 6.5%, so 1.065 raised to the 13th power. So that cuts the cost in half, roughly. But in addition to that, there were enormous benefits associated with improvements of reliability. In fact, we estimated that they could, if engaged in optimal operations and made all the investments that we recommended, that they could reduce 46% of the customer minutes of interruption on Nantucket Island. So a potential huge benefit there. And then benefits of market operations. As a result of FERC Order 841, which is improving the performance of the energy markets to invite more participation of assets like energy storage systems and level the analytic playing field in terms of how those streams are valued. ISO New England has implemented something called the continuous storage facility option. So the question is energy storage a generator? Is it a demand-side resource, or is it a regulating resource? And of course, the answer is yes to all three. It can be all three simultaneously, or at different times throughout the day. And so you have to devise a structure that can account for all three benefit streams. And so you can see that in the chart to the right there. You can see an energy-neutral AGC signal that's sent to the energy storage system there with that blue line that's regulating up and down across the zero axis. At times it's providing energy, and you can see that yellowish line there where it's providing energy, and if you're discharging energy, then there's a positive net flow of energy onto the grid. And then at other times it's a demand-side resource because it's absorbing energy. And you can see when those three signals are combined, the outcome of that to the lower right. And so it gets this very unique signal sent to it, and it's compensated accordingly. There's telemetry to ensure that the energy storage system is actually providing all of these services when asked to do so. And so we were able to model this. We assumed imperfect knowledge, so we predicted the prices that would be evident in the market rather than assuming perfect foreknowledge. We did not assume a perfect operation from the perspective of the energy storage system. It's temperature dependent, and so the round-trip efficiency fluctuated. And so building all that in, I think, yielded a very realistic simulation. You can see the market benefits at about $24 million, the vast majority of which were tied to frequency regulation. And when you add this all together, you have a return on investment ratio of 1.55, with the benefits of 145.9 million, vastly exceeding the present value costs to the customer, to both the CTG and the battery system, and then all of the additional adders that have to be factored in. There's insurance costs, there's O&M costs, there are debt costs, and all of that was woven in to this $93.9 million price tag. And all of that has to be accounted for in your cost analysis. So here are the results of several recent studies, and what we find is that energy storage systems don't always pencil out. And economists have a bad reputation of always generating benefit-cost ratios that exceed 1. And I think we do a very good job of simulating the benefits in a very realistic way and generating what I think are scientifically defensible results. And when doing so, several of our studies will generate ROIs that fall short of 1, and when they exceed 1, hopefully you can count on the reliability of that estimate. So with the Salem Smart Power Center, using that high cost of $20 million plus, the return on investment ratio was quite low. Puget Sound Energy Glacier, the vast majority of the benefits accrue to the local customers because it's a battery system on a low reliability circuit near the Canadian border where there's a small community that can be entirely islanded. So I think it's only about 20 to 30 customers, residential customers, and 20 to 30 businesses. But still, that's a significant value to those customers. Opauco Decatur Island, that would be located on Decatur Island in the San Juan Islands and off the coast of mainland Washington. And there what we studied was the ability to use energy storage to reduce the voltage and stress that's placed on submarine cables. And by doing so, you can lengthen their lives. So if you've got a cable that costs $30 million or $40 million, if you can extend its life by 3 or 4 years by reducing the stress placed on that cable system, you know, there's enormous benefits associated with that. Northampton microgrid to the right, that was tying together a Department of Public Works, Cooley Dickinson Hospital, and what would be the Red Cross shelter, which is the local high school, and benefits exceeding costs there because of the capacity benefits and the reduction in bill associated with demand charge mitigation. We've also, well, I'll tell you about Avista Turner first, and then I'll come back to our microgrid assessment capabilities. So Avista Turner, as you can see from the perspective of the utility, the return on investment ratio is quite low. But the benefits to a single technology-based customer, Schweitzer Engineering Laboratories, could be quite enormous. Effectively, at Schweitzer, there are 1 to 2 voltage sags per year that cause their machines to shut down. Once their machines shut down, it takes at least 3 hours to come back online at a cost of $150,000 per hour of lost production. And so that's $1 million, roughly, each year of benefits associated with avoiding that downtime. And so the battery that we were evaluating there demonstrated a capacity to provide this service, but ultimately isn't providing this service. And I'll tell you why. Something you learn through this process is when you're deploying new technologies that are novel in nature and quite advanced and new and emerging and nascent, there are times when they fail. And so the battery system there, which was a new vanadium flow battery system, a technology that was actually spun out of my laboratory, Pacific Northwest National Laboratory, it failed. So it incurred some challenges in operations and had to shut down and has ultimately been disassembled. The same has been true for some technologies applied elsewhere. So lithium-ion battery systems tend to be a bit more mature, and there's a bit more certainty in their operation, but they face safety challenges and degradation challenges. And so Department of Energy is supporting the development of new technologies to address some of the challenges embedded in traditional lithium-ion technologies, which benefited from expansive application in the consumer and automotive sectors. So there are benefits there from a technology maturation perspective. So finally, I just wanted to mention with respect to microgrids, we've developed a microgrid tool that effectively can evaluate the reliability benefits associated with adding new assets. So microgrid, of course, is energy assets deployed behind the meter at a location. It could be in front of the meter if you can actually island the location, but effectively you can pull away from the main grid an island in location. So you can add a photovoltaics or solar, diesel generators and energy storage systems, and improve reliability. So if there's an outage, you can continue operations. And what our system does is it values the improvements in reliability and the economic operation of the system. So we can answer a couple questions. And that is, if we have $5 million, how could we invest them in terms of net costs of the system, so benefit cost minus the benefits in present value terms? How would we invest this wisely to maximize our resiliency benefits? We can answer that question. Or we can answer the question of, if we want to set our target at 90% reliability for up to, let's say, 2 weeks, how could we invest in assets so as to minimize net cost? And so we can answer those sorts of questions. So it's kind of playing between the economics and the reliability. Now, we've talked about valuation and benefits so far. Now, let me focus on cost for a moment. As many of you have heard, the cost of photovoltaics or solar has been dropping quite quickly, and so too have the costs associated with lithium-ion technologies. And so you can see the declining battery prices. So this is for the cell and the pack falling from $599 per kilowatt hour to $273 in 2016. And in fact, we're seeing prices below $200 per kilowatt hour in 2018. An important note is that that's only a portion of the overall system cost. You have to interconnect this asset to the grid, develop control systems, add power conversion systems from AC to DC and back to AC. There's construction and commissioning costs. And that will double the costs associated with the battery system at least. And those costs aren't falling as quickly because those are more mature processes. If you're constructing a substation or the pad for a battery system, the costs are going to look fairly similar and might actually grow over time. You're not finding as much innovation there as you are with the battery system. So while the prices are dropping, the overall system prices from the utility perspective are not dropping as quickly, and they are not always completely captured in all the cost estimates that you hear in the literature. We recently evaluated the costs associated with 6 battery systems here. You can see in the table, and you can see the total project cost. That includes the 4 components I mentioned previously. So that cost includes the pack and the cell costs and capital costs, the power conversion system costs, balance of plant costs, and construction and commissioning costs. You can see here for lithium ion, the costs at $469 per kilowatt hour. The 362 in parentheses is our projection out to 2025. We've also got a number of performance attributes characterized in this study, which is cited to your lower right there, Mongard et al., including round-trip efficiency, lifespan, number of cycles, degradation rates, and the lot. Also pumped hydro, but also compressed air energy storage systems, flywheels, and ultracapacitors. Combustion turbines are also characterized in this study as well. And so you can see the lower costs per kilowatt hour for pumped storage hydro. It's an enormous asset, so it has huge energy capacity and overall low costs because it's a mature technology, and the costs are not falling as quickly. Okay, so now that you understand the costs and the benefits associated with energy storage applications, you have to understand how the battery systems perform. And this is essential for capturing the value in real time and characterizing it correctly when simulating performance and designing the systems. So the way we do it at Pacific Northwest National Laboratories, we typically start with the DOE, Office of Electricity, Energy Storage Testing Protocol. And we run it through a series of tests to establish a baseline from a performance perspective. Then we define a number of use cases. So what does arbitrage look like for this system at this location for this utility? And we create a duty cycle for the energy storage system to follow for a 1-week period. The same thing with respect to frequency regulation. So we try to make it as realistic as possible. We run through all those use cases back through the DOE OE test protocol, and then sometimes we'll do it, we'll perform tests interseasonally. And so we'll go back, cycle back through 2 or 3 times to yield as sophisticated results and accurate results as we possibly can. So for the Washington Clean Energy Fund, we evaluated energy storage systems at 4 sites in the Pacific Northwest, all in Washington State. You can see vanadium flow battery systems at Avista and at Snohomish Public Utility District with varying energy to power ratios and scales. Collectively, we have 7 megawatts, and it looks like about 16.2 megawatt hours. This was $15.3 million of investment from the state, matched with utility investments and DOE investments that made the total investment in excess of $43 million. And we have 2 lithium-ion battery systems that we're evaluating at Snohomish PUD and Puget Sound Energy. And what we found is the battery system round-trip efficiency varies quite significantly from one technology to the next, and was a bit more certain from the perspective of lithium-ion battery systems, less so from for the vanadium flow battery systems. And so you can see this uncertainty reflected in some of the tests that we performed. This is just a simple test showing a low rate of output, moderate rate, and high rate of output. You can see for one lithium-ion battery system, the round-trip efficiency went from a low of 69% all the way up to 90%, while the other at Puget Sound Energy was much more uniform, from 83 to 90%. And the flow battery systems yielded lower round-trip efficiency rates, and we found when testing under certain conditions that the round-trip efficiency could fall even quite a bit lower, down into the 40% range, into the 40s. And so it's important to adequately and accurately characterize the performance of these energy storage systems. We also found the round-trip efficiency for even a single lithium-ion battery system could differ quite significantly. Here's the Puget Sound energy battery system, and you can see the round-trip efficiency falling quite low for a very specific set of tests, and then rising up towards 90%. And you can see that it varies mostly based on temperature and the type of use case that you're using. So some where there's a lower power output level and auxiliary loads are a larger share of the overall round-trip efficiency calculation. And when you're at low temperatures, it tends to yield lower round-trip efficiencies. Now this chart is a little misleading because this test was performed near the Canadian border, and the temperature really didn't get much above 80 degrees. Now, in reality, what you would see if we had tested up to, say, 105 degrees is that we reached a sweet spot here, and at some point, the round-trip efficiency would have begun to fall again. So it wasn't just a system that would keep growing or leveling out. It would actually begin to fall again as the temperatures rose. So as you can see from this chart, what it shows is the observed values in the circles overlaid these lines that are the predicted values. And what you see in any given system is that when we begin our testing of the system, we're fairly inaccurate in our estimation process. And so when we first began testing some of these battery systems, we had to operate within state of charge limits, let's say 10%, 90%. We find ourselves outside of those state of charge limits fairly rapidly, within a day or two, because we could not accurately predict how the battery would perform. But as we collect more data and information, we could accurately predict how the battery performed, and you can see the curves falling on top of each other. What we found is that the battery system's performance varied based on four variables, statistically significant variables. These were power output level, state of charge range within which you're operating, whether you're charging and discharging or discharging, and temperature. And each of those affected the performance of the battery system. And we were collecting enormous amounts of data, 80 to 140 data tags flowing through a filter and as granular as a second-by-second basis. And so the coefficients for each of these variables could be continuously updated. And through machine learning, we were constantly improving our predictive capacity. And with that, we learned we can generate much more value for the grid. So if you have an economic assessment that has perfect foresight, perfect information, and is generating estimates of $1 million or $2 million per year in the real-time market, you know that you're probably vastly overstating the benefits. And so rather than estimating an ROI of 2.1 or something and then generating in real time return on investment ratio of 0.6, we're hoping to generate return on investment ratios of 1.1 and then actually capturing that 1.1 in real time. So we're aiding with the development of control systems and improvement in the assessment of the actual expected performance of the battery systems. And what this shows you is for this one location, although it's quite a low value stream because arbitrage in the Pacific Northwest, the Mid-Columbia is a relatively low energy market with very few broad swings between off-peak and peak prices, that it's a low economic value. But using the nonlinearity in our modeling procedure, we actually generated much more value because we could charge the battery system in sweet spots so as to maximize the efficiency of those operations. And then we only operated the battery when we were certain that we could generate profit. So we were operating in economic sweet spots and generating much more value than if we were clumsily estimating benefits and then operating at times when we don't understand the battery's performance or are over-predicting the revenue associated with prices in the Pacific Northwest. So we've been developing control algorithms. In terms of developing control strategies, sometimes we're on sort of the ground floor, helping utilities develop new control strategies holistically for their systems. In other cases, they've already developed control systems or purchased a third-party system from a vendor, And what we do is we apply something called the Optimization Performance Evaluation Tool, or OPET. And what we found is that utilities, when engaged in economic operation using either third-party vendor systems or systems that they've already deployed out in the field, sometimes their operations in real time fall short of optimal output from an economic performance perspective. And typically, there's three reasons for this. One is a lack of understanding regarding the battery's performance, and we found this to be quite a significant component. There are cases when the utility is expecting 90% round-trip efficiency when they're actually getting 68% round-trip efficiency, and they expect significant economic returns when they're actually losing money because of those losses. Another is logic. So we worked with a utility that was using a battery system with 10 to 30% round-trip efficiency losses, depending on when it was used and how it was used, to avoid a 10% penalty in balancing their system from Bonneville Power Administration. Now, you would never want to use a system in that manner because you have to account for those round-trip efficiency losses in your control systems. Also, you want to base your market operations on predictions of prices, not predictions of load, for example. We found some control systems that effectively operate based on predictions in load. And then the final one is, of course, prediction error. So to the extent that utilities are struggling to predict prices and engage in real-time market operations in an optimal manner, their returns fall short of what they could have otherwise yielded in real time. So we take this tool, you use your system for a week to a month, and then we simulate that same time period using our tool. And we can break it down. You know, what you estimated at X, we estimated at 2.2X over that 1 month period. And the difference is this. It's mostly tied to your lack of understanding of battery operations and capabilities, but also we can account for the imperfect forecast and the knowledge error as well. So the idea is to help propel industry forward in a way that improves these systems over time. So a few lessons that we've learned is that, you know, performing these assessments before you build and deploy the systems is extraordinarily important. Siting and sizing of energy storage is key to yielding a positive return on investment in a good project. You have to evaluate a broad set of use cases, but typically realistic scenarios boil down to a smaller number of use cases, say 2 to 4 use cases. You have to simulate those use cases and co-optimize to present something that is technically achievable. There's regional variation. So what's important in one region and what generates value is going to be very different in another. And utility structures, even within the Pacific Northwest, if you're a public utility district or a co-op or vertically integrated investor-owned utility, then the value streams differ quite significantly, and how you operate that battery system will differ quite significantly as well. And so the battery characteristics that I've stated several times are also very important. Characterizing that, building it into your economic operation, in your modeling and in your real-time operation to optimally utilize your battery system to take maximum advantage of the landscape of economic opportunities is key and is rarely captured. So what are we doing at Pacific Northwest National Laboratory to address some of these key challenges? I mean, once again, I've stated repeatedly that historically the value of energy storage for specific applications has often been vastly overstated, but many use cases are not completely covered. And so we're expanding our models to capture more use cases, to simulate operation in a more realistic manner. We're including non-battery technologies, including pump storage hydro, power to gas, hydrogen fuel cells. We're working with other national laboratories to improve our capacity in this area. We're evaluating how market penetration rates ultimately could change as you lower the cost associated with energy storage technologies. And we hope in the next year or two to develop a tool that you could deploy in a balancing area or region of the U.S. and answer the question of how much energy storage is optimal today and 5 years from now, and where would you put it to yield a positive economic return. And then we're taking all these lessons, we're reaching out to regulatory authorities and to markets to help level the analytical playing field and the market playing field for energy storage assets. And we've got significant lab resources at Pacific Northwest National Laboratory that are trying to improve performance and bring down the costs using new materials and advanced chemistries. And we're trying to put this all together to really propel this important industry forward in the coming years. We really think it's going to be essential for the future distributed green grid of the future to maintain reliability and maintain reasonable costs as the grid requires more balancing resources and more flexible resources to improve reliability. The last thing I want to mention is I want to acknowledge the leadership that's been provided by Dr. Imre Zsuk at the U.S. Department of Energy. He is the head of the DOE OE Energy Storage Office, and Bob Kirchmeier, who's the head of the Clean Energy Fund Grid Modernization Program at the Washington State Energy Office. And then finally, on the last slide, you can see my information. Feel free to reach out to me via email or give me a call. And we have a site there, energystorage.pnnl.gov, where many of our publications are found. And you can download those and take a look at those. And I hope this was helpful. And feel free to reach out to me if you have any further questions. Thank you.